For this particular kind of problem, we're dealing with the standard 8.F.4, which, as you can see, this is where we are perhaps going to construct a function to model a linear relationship between two quantities. Sometimes we may only be asked for the rate of change, like in this particular problem. Other times we might be asked questions in addition to that, maybe about the initial value, or other times maybe coming up with a linear equation that will represent that situation. So in this particular problem, we have a table. And as it says, this table shows a linear relationship of the water level in a tank and time. Complete the sentence below that represents the relationship. And so basically what we're trying to figure out is, if I click on the drop-down box, the water in the tank is either increasing or decreasing and at a rate of whatever. So we basically, if we find the rate of change, we'll know whether the value is increasing or decreasing, because a positive rate of change would mean more water is going into the tank as the time goes by, and decreasing if water was sort of leaking out of the tank. So let's go ahead and find the rate of change. So as usual, it's the change in y values over the change in x values, or maybe the change in the output over the change in the input. So to go from 54 to 56, we are adding 2. To go from 2 to 3, we are adding 1. Therefore, rate of change can be also thought of as slope. We have a change of output of 2 and a change in input of 1, which means that the tank has a rate of change of 2 gallons for every minute. So every minute that goes by, the water in the tank is increasing at 2 gallons per minute. So now we have enough information to answer the question. The water in the tank is increasing at a rate of 2 gallons per minute. Continuing with the types of problems that encompass the standard 8.F.4, where we are perhaps constructing a function or maybe being asked questions about the rate of change or initial value. Well, in this particular problem, Darius is measuring the depth in centimeters in his fish tank at the end of each day, and his measurements are shown in the table. So we're supposed to enter an equation that shows the water depth y in the fish tank after x days. So in order to find an equation of any linear situation, we would need the slope m and the numeric value of the y-intercept. Well, slope is the first thing that we'll find. So we have the change in output. To go from 14 to 13.75, we have to subtract 0.25. And over the change in the input, to go from 1 to 2, we're adding 1. So that means the slope is 0.25 over 1, which is negative 0.25. Now, as far as the y-intercept goes, it's not found in our table. So what we'll have to do, and we have to do this sometimes, we have to work backwards in the table. So what I mean by working backwards is we know we need the ordered pair 0, comma something. So we already know that the change in x values, or excuse me, the change in y values working down the table is subtracting 0.25, and we are adding 1 to the x value. Well, to work backwards, we would do the reverse or the opposite of that. So to get from 1 to 0, we have to subtract 1. And to get from whatever we have, which is 14, to the value we need, we would have to do the opposite of what we were doing working down the table. And we can see that that is adding 0.25. So 14 plus 0.25 is 14.25. So now we have the numeric value of the initial value. And so if we put both of those things together, we then have our equation in the form that we need. So once again, y equals negative 0.25x plus 14.25. So let me go ahead and clear off all of my work here. Y equals negative 0.25x plus 14.25. Continuing with standard 8.F.4, where we are trying to construct a function from the relationship between two quantities. Here we can see we have a table, and we're trying to come up with the function in the form y equals mx plus b. So, of course, that means that we need the slope, and we need the b value of the y-intercept. Well, fortunately, the b value for the y-intercept is right there. So since the y-intercept is found at the ordered pair 0, 2, we know that the b value is 2. So now we need the slope. And we'll do what we've done many times, which is finding the change in y over the change in x. So the change in y to go from 10 to 6, we have to subtract 4. And the change in x is going from negative 4 to negative 2. We have to add 2 because negative 4 plus 2 is negative 2. So the change in y over the change in x is negative 4 over 2, which simplifies to negative 2. So we see that our slope is negative 2. So that would give us the linear function y equals negative 2x plus 2. And I'll go ahead and clear off my writing here. Y equals negative 2x plus 2. Continuing with standard 8.F.4, where we are trying to construct a function to model a linear relationship between two quantities. Here we can see we have a table of values that we are being told represents a linear function. And so we need to come up with an equation to represent that function. And of course, as we can see from the values in the table and the variables that are defined within the table, we're going to be writing it in the form y equals mx plus b. There are times where we luck out and the y-intercept happens to be in the table. The y-intercept is there at 0, 3, which means that the b value is going to be 3. So now to find the slope, as we've done many times, it is the change in y value, which happens to be, to go from positive 3 to negative 3, we have to subtract 6. To go from x to positive, or from 0 to positive 3, we have to add 3. Negative 6 over 3, or remember, it's change in y values over the change in x values, simplifies to negative 2. So now we have our linear function, which is y equals negative 2x plus 3. Continuing with the standard 8.F.4, where we are trying to construct a function to model a linear relationship between two quantities, there are times in this standard where we may only be asked for the rate of change or the initial value. But in this particular problem, we can see that we're only asked to find the rate of change. Remember, rate of change can be thought of as the slope. So to find the slope, it is the change in output or the change in y values. These would be the y values. These would be the x values. To go from 1.80 to 2.70, we are adding 90 cents or 0.90. And the change in x values, we are adding 1. So the change in y values over the change in x values is 0.90. And what that means in the context of this problem is that for every snack packet that you buy, it's going to cost you another 90 cents. So the rate of change is 0.90 or 0.9. Continuing with standard 8.F.4, where we are trying to construct a function to model a linear relationship between two quantities. In this particular problem, we're given a graph, and then we're asked to complete 4 parts to that graph. So if we look at part A says, what is the slope of this line? Well, we'll need to find 2 perfect ordered pairs. So I'll pick a point right there at the y-intercept. It looks like we have another good one right there. So we are rising 2 because we're going in the upward direction, but we are running a negative value because we are going to the left. So we can see that our rise over our run simplifies to negative 1/2. So we have a slope of negative 1/2. We should have known that the slope was going to be negative anyway because the line is going downhill from left to right. Part B, it says, what is the numeric value of that line? Well, as we can see on the graph, it's going through 0, 2. So the numeric value of the y-intercept is positive 2. Now, part C says line P, which is not shown, has the same slope and passes through 0, negative 1. Which table represents the 5 points? Well, as we can see from all of these tables, we can see they're all going through that point already, so we don't even have to pay attention to that. The key here is we're trying to figure out which one of these tables also has a slope of negative 1. So let's take a look at that. So I'm going to not necessarily go in order so that I don't have to deal with decimal values, and it is okay to do that. So for example, I could take those 2 since we have only integers there. And to go from negative 2 to positive, or negative 2 to negative 1, we have to add 1, change in y values over the change in x values. So to go from negative 6 to positive, or to 0, we have to add 6. Well, clearly, m is not negative 1/2 in that table. So I'm going to continue working my way down the tables, and I'll use the same strategy to go from positive 2 to negative 1. We have to subtract 3. To go from negative 6 to 0, we have to add 6. And so we have negative 3 over 6, which is negative 1/2. So already I have now found the table that has the same slope as the graph line up above, and also goes through that point 0, negative 1. So that would be that. And it's asking us for the equation of that line. Well, it would be, we know the slope is negative 1/2. And we already knew the y-intercept. If you look at the table, we have 0, negative 1 in the table, so that means the y-intercept is at negative 1, or that's the b value of that y-intercept. Continuing with the standard 8.F.4, where we are trying to construct a function to model a linear relationship between 2 quantities. In this particular problem, a leaf falls 28 feet from a branch to the ground at a rate of 5 feet every 2 seconds. Well, we could kind of think about this as a linear function. And if the leaf started at 28 feet from a branch above the ground, we know the initial value is positive 28, and it's falling to the ground at 5 feet for every 2 seconds. Well, that would mean that our slope is 5/2. Now, sometimes doing things like that will allow us or help us to answer the questions within the table. So the initial height of the leaf is 5 feet. Well, clearly that's not true because it is 28 feet. The leaf falls at a rate of 5/2 of a foot for every 1 second. The slope clearly tells us that, or the rate of change. The leaf is 24 feet above the ground after 2 seconds? Well, time happens to be the x value. The amount of feet after the time happens to be the y value. So we could do something as simple as this. We're going to take, in our function right here, we're going to replace y with 24 and x with 2. And we're going to see if that answer is true. Well, we can do a little bit of math here, and clearly 24 is not equal to 5 plus 28. So that one would be false. So it looks like we've got false, true, false. And of course, this problem alternates. It's not always false, true, false.